Okay, today's the last day for the qual analysis lab, so I want to talk about the report for this and also some of the chemistry that's happening here. Hopefully this is readable. Qualitative analysis report. Report's going to be kind of simple. What we're going to do is we're going to have the unknown number, and then we're going to just list the cations that you got a positive test for. So cations found, however many. And then we could do a bonus here. The bonus would be if you do an anion test on your unknown sample. Not today. I still have some people that, I think one person needs to take it. So Wednesday, it's looking like. All right. To make all the points not wrapped up in this, I want you to do one other thing. I want you to list the chemical reactions that were observed. And so chemical reactions, not the chemical reactions for your unknown, but chemical reactions for the qualitative analysis procedure. So let's take a look at the procedure here, and then we're going to look at the chemical reactions that occurred. So the first, we have these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 species. And then we reacted with HCl here. And then we're going to look at the chemical reactions that occur with reaction of HCl with these 10 species. And so what I'm going to do here is I'm going to just do this in the same format here. That is, we'll have our species here, ammonium, silver, we'll get in the same order, iron, aluminum, chromium, iron 3, aluminum, chromium 3. These are 3+ cations. Then we had some 2+ cations here, which were calcium, magnesium, nickel, and zinc. Calcium, magnesium, nickel, and zinc. And then we had the 1+ cation, sodium. We also have ammonium, which is also a 1+ cation. And so the first step here was to react it with HCl. And so what were the reactions that we expect to occur? Well, out of all these, only silver reacts. And so I'll just write here, silver ions plus HCl. This is going to react to form silver chloride and H+. H+ is just a spectator, H+ or hydronium. In reactions like this, I use H+. In other reactions, when we're dealing with pH and that type of stuff, I use hydronium exclusively. And so it's the chloride that reacts here. So HCl has different chemical properties. A lot of them are associated with its strong acid property, but not all of them. In this case, we're looking at the metathesis properties of HCl, not the acid properties, because the acid is a spectator in this case. We can also look at the redox properties too, which H plus doesn't neutralize bases, but oxidizes things. But what that means is this, okay, we end up with this precipitate here, which is a solid. Sometimes people write a down arrow here to show it precipitates. Sometimes you'll see that. But the other species, like for example, ammonium, ammonium has already got a proton, it's not going to want another proton, so plus HCl. This yields NR. There's no change here, ammonium. What about iron 3? Iron 3 plus HCl or chloride yields no reaction. It forms a soluble salt. And so iron 3, NR plus HCl. Maybe I should write it out. There's no driving force here. So aluminum forms aluminum chloride. Aluminum chloride is soluble, so we aren't going to get any precipitation. Then we go chromium 3 would form chromium 3 chloride. Chromium 3 chloride is also soluble. It's not going to precipitate. So we get NR here. Calcium would form calcium chloride. Calcium chloride is soluble. Magnesium would form magnesium chloride, which is soluble. Nickel plus HCl forms nickel 2 chloride, which is soluble. Zinc, HCl is going to form zinc chloride. Zinc only has one charge. It's always 2 plus. It's a pseudo group 2. Depends on the periodic table. Let's see if this periodic table shows it as pseudo group 2. No. Some periodic tables, this is pseudo group 1, like the alkali metals here. And this would be pseudo group 2. In some periodic tables, we label these Roman numeral 1 and Roman numeral 2. These are 1A, 2A. This is labeled 1B, 2B in certain periodic tables. But zinc is always 2 plus. And so this is reactive. And sodium ions would form sodium chloride, and sodium chloride is soluble. So the only thing that's going to react is this, which forms a precipitate in this metathesis reaction here. We can take a look at the KSP value for silver chloride, and we can actually calculate solubility. The solubility in this case would equal the square root of the KSP. And then when we figure out how many grams or how many moles, it's like 10 to the minus 6 moles. It's very small. A little bit does dissolve. And so when we say complete separation, what are we talking about? Well, complete precipitation, when I say complete precipitation, I just mean what? Greater than? Well, that's 0.1 remains, but 99.9% is precipitated. And so we're going to get greater than 99.9% of this to precipitate out. It should be pretty easy. That leaves such a small amount in the decantate, it's not going to interfere with subsequent tests. If you leave large amounts of silver in the decantate, then what happens is it interferes with other analyses. So we end up with a white precipitate of silver chloride here. Okay, in the next step, we dissolve the white precipitate using ammonia. And so here, we'll follow this branch over here. You know, we have to clean this precipitate because this precipitate is going to be contaminated with all these other ions in solution. So we need to clean the precipitate. We're assuming I already cleaned it. You know, in other words, wash the precipitate. And then here, we're going to add ammonia to dissolve it. So there are two ways we can analyze this. We could do this qualitatively. If we do it qualitatively, we're looking at silver chloride solid dissolving. Silver chloride solid dissolving in water has minimal solubility. We already calculated. The KSP is very small. It's like 10 to the minus 10. In fact, let's look at the number here. It's 1.8 times 10 to the minus 10 there. And so that's quite small. 1.8 times 10 to the minus 10. And how can I get it to dissolve more? You know, because its solubility is quite low. And so not much dissolved. I mean, we're looking at like micromole or something like that. Or micrograms. I think it's like a microgram in a liter or something. So it's very small. We could calculate it out, and I think I did calculate it out earlier. I just don't remember the number calculated. But is there another way to get more of it to dissolve? Yeah, add more water. You know, that's one way. If we add more water, we're going to make the solution more dilute, right? But if you wanted to get, let's say, a lot of it to dissolve, let's say you had more than a microgram, you know, let's say you had like 100 milligrams. You know, 100 milligrams of a typical solid is like a match head's worth, you know, small match head like we have. That's about 100 milligrams or a tenth of a gram. Let's say I wanted to get 100 milligrams to dissolve. How much water would I have to add? I have to add a lot of water, right? A lot of water. So that's one way to get the silver chloride to dissolve. Just keep adding more and more water, and eventually it'll dissolve, but you're going to have to add like a huge amount of water. And so what we're looking at is we want to shift this equilibrium to the right. Well, we could shift it to the right by just diluting it and then changing the concentrations. And the concentration is no longer going to match KSP, so it's going to become unsaturated. But there are other ways to shift this to the right. How else can I shift this equilibrium to the right? Well, one way is decreasing the concentration, but is there another way of decreasing the concentration other than diluting it? There is. If I can react these chemically with something. So for example, if I can remove, let's say if I can remove the chloride, what are the ways of removing chloride? Well, removing chloride, we need to know the chemical properties of chloride. You know, can you think of some chemical properties of chloride? It's a reducer. It's not a very good reducer. You know, it's very stable towards oxidation. It's hard to oxidize chloride. You can do it though. We often do it, like for example in the laboratory, we want to generate small amounts of chloride. I mean not chloride, chlorine. We want to generate small amounts of chlorine gas using chloride. So how can I oxidize it? Well, typically in the lab, what we do is we just add some potassium permanganate. Permanganate's a great oxidizer. So you mix chloride with permanganate, you're going to generate chlorine gas. And so it's an easy way to generate chlorine gas. But chloride's not a very good reducer. So we could add potassium permanganate to this. The potassium permanganate will attack the chloride and convert it into chlorine. And as the chloride concentration decreases, that's going to shift the equilibrium to the right according to Le Chatelier's principle. But working with potassium permanganate is, it's a strong oxidizer, so we try to avoid working with strong, powerful oxidizers if we can. So that's one thing. Another thing is we could try to precipitate out, we could set up a competition, silver ions versus some other ions. So for example, chlorides are all soluble except for silver, lead, and mercury. So what we could try to do is we could try to add some lead ions in here. If we add some lead ions, then there's going to be a competition for the chloride between silver and lead. Who will win? Who will win would be the one that's less soluble. So we could precipitate out lead 2 chloride, or we could precipitate out silver chloride. In this case, silver would win because lead is more soluble. Although it's a bit more tricky because in terms of solubility, when we're looking at KSP, we can't just compare the KSP. So for example, when you look at the KSP for silver chloride, it's 1.8 times 10 to the minus 10. But if we look at the KSP for lead 2 chloride, it's 1.6 times 10 to the minus 5. 10 to the minus 5, that's a lot bigger. So that means a lot more ions get into solution. The ion product is equal to this. And so it looks like this, but the problem with a direct comparison of the KSPs is because they split up differently. Lead 2 chloride splits up into 3 ions. When it splits up into 3 ions, then the solubility relationship is KSP divided by 4. The KSP relationship is different. And so when we look at the solubility, let me write it down. Be safer that way. This will just be a side topic here. For something like lead 2 chloride solid, that's going to split up into 1 lead ion and 2 chlorides. And so if we do an ice table here, we say 0 and 0, and then this is plus S and plus 2S, and then we get S and 2S. And this is going to equal, the KSP is going to equal the lead concentration, which is S, times the chloride concentration squared, which is going to be 2S quantity squared. And so actually the solubility relationship here is it's going to be the square root of the KSP divided by 4. Whereas silver chloride splits up differently. Silver chloride splits up into 1 silver and 1 chloride. And therefore, this is just going to be S and S at equilibrium. So initial 0, 0, change is plus S, and at equilibrium we're going to just see S and S. So in this case, KSP is equal to silver concentration, which is S, times the chloride concentration, which is S, which is going to be S squared. And so S is just going to equal the square root of the KSP. So we have to be careful. But, we have 5 orders of magnitude difference here. It turns out the lead is much more soluble. When you do a precipitation of lead, there's still a lot of residual lead left in solution. You can't precipitate all of it, and it's a significant amount. So lead is fairly a fair degree more soluble than something like silver. But we don't have any lead here, so there was no competition. We used to have a more difficult procedure. We could try mercury. Maybe mercury would provide silver with more competition. And so if we look at mercury, mercury 11 chloride here is 10 to the minus 18. And so this one splits up differently. Mercury 1 chloride splits up into what? How many ions? This would be more like Chem 1A. Mercury 1 chloride splits up into how many ions? 4, 3. Actually, 3 is correct. That's because the mercury one is diatomic. This thing's held together by a covalent bond. It's a mercury-mercury bond. Forms a diatomic cation. And so this would have a splitting pattern the same as lead. So the solubility is equal to the square root of the KSP divided by 4. So we can compare the 3 solubilities, and it turns out that mercury is going to have the lowest solubility. So if I put mercury in there, that would set up a competition. What's going to happen is this. If I put in mercury in here, into the mix, then I have a competition between silver and mercury. Mercury would win. Eventually, what's going to happen is all the silver chloride is going to be converted into mercury 1 chloride. That's called a solid to solid transformation, where we set up a competition and the less soluble one wins. I don't want to do a solid to solid because you're replacing one white solid with another white solid. And it's going to be hard to tell if anything happened, right? So we're not going to do that, although it would work. So let's focus maybe on, the acid-base properties of chloride are not really significant. When we think about the Bronsted base properties of chloride, what would you say about the Bronsted base properties of chloride? Is chloride a decent base? Let's say you ran out of antacid at home. Could you substitute chloride like salt, sodium chloride? Will it work as an antacid? No, it's not. Chloride is neutral. As a Bronsted base. However, as a Lewis base, it might not be so neutral. As a Lewis base, it might be effective. Now, we haven't covered that many Lewis base, acid-base reactions, but we know that chloride can act as a ligand. We call it chlorido. So we can see it here. This one. This is called trichloro or trichlorido cuprate 2 ion. And that has a KF of 10 to the 5. So that likes to form a stable complex there. Let's see if there are any others. So maybe we could add some copper 2 ion in there. The chloride attacks the copper 2 and forms this complex as a Lewis acid-base reaction. That's possible. But I don't want to add copper 2 to this. Nor would I want to add cadmium. We have the tetrachlorido. Actually, this is a typo here. There shouldn't be any parentheses here. Tetrachlorido cadmium. But, it's an anion, so we call it tetrachlorido what? Or tetrachloro what? If you could name all the species on here, that would be pretty good as a review for chapter 25, maybe 24. Cadmiate. But anyway, that's 10 to the 2. Maybe that would work. We have these. This one's pretty good. This tetrachloroplatinate 2, 10 to the 16. This is quite good here. So chlorido can act as a Lewis base and attack metals like this. Not all metals, but it's possible. And now it's going to reduce the free chloride concentration in solution. So we can see what chloride likes to attack based on this table here. Not that many species here. Sounds like a horror movie or something. Anyway, getting back to this, the silver ion, though, can be attacked as well. So the silver ion, we don't think of this as having much in the way of Bronsted acid-base properties. In fact, Bronsted acid-base, we wouldn't even consider silver ion. Some of the higher charged ions could act as a Bronsted acid-base. Like, for example, the aluminum 3+, iron 3+, those are decent Bronsted bases when they form aqua complexes. But for this, what should we attack silver with? What would be the best base to attack silver ions with? Which one? Ammonia? Why ammonia? Ammonia is not the strongest. What's the strongest out of these? What would be the most effective way of dissolving silver chloride, that is pushing the equilibrium to the right? Which would be the most effective at reducing the free silver ion concentration? Cyanide. Yeah. Cyanide would be the best, but we don't have any in our lab, so considering what we have in our lab, probably the best is going to be ammonia. Ammonia is not going to be as effective, 10 to the 7th versus 10 to the 18th, but it's going to work good enough. We'll just have to add more ammonia than we would have had to add for cyanide. Cyanide, we wouldn't have had to add very much. So in terms of qualitative, what we're going to do is we're going to decrease the free silver ion concentration by adding ammonia. How many ammonias do we add? We'll just read it off the table. We are going to add 2 ammonias. We're going to have silver. With 2 amines attached to it. It's going to be 2 plus. Kf was 10 to the 7th. (1.6 times 10 to the 7th). Kf is very large. 1.6 times 10 to the 7th is quite large. So qualitative, what we're doing is we're attacking the silver ion, and we expect this to shift right. Because what we're doing is we're reducing the silver ion concentration by attacking it, or removing the silver ion by attacking it with ammonia. So this shifts right. All right, what about quantitative? If I want to do this quantitatively, how would I do this? Well, I have a special scenario. I have to do this, of course, I'd have to do this simultaneously, right? All multiple equilibria I should do simultaneously, but hopefully I could do it stepwise. Could I do this one stepwise? Not really. You can't do this one stepwise, unfortunately. It doesn't quite work stepwise. Could I do this simultaneously? It's going to be tough. And so what we have is we have this scenario that comes up when the step 1 has a very small K. A very small K means, do we generate much product? No. And step 2 has a very large K. So number 1, we generate a minimal amount of product here, and number 2, that product that we generate is immediately attacked in step 2. Means that we can use the combined method. The combined method is when we have a scenario where we have a very small step 1 and a very large step 2. Very small step 1 and a very large step 2. Then the combined method works. The reason the combined method works is because of this. When we add up the 2 equations, silver chloride solid plus 2 ammonias, the silver ions cancel one another out, yields the diamine silver complex and chloride. What species is missing? What species is missing is free silver ion. Free silver ion's missing. But that's okay because the amount of free silver ion should be negligible. So if we can ignore the concentration of free silver ion, then it's fine. Which we should be able to do in this case because we generate so little and it's consumed immediately. And so even though this doesn't show the free silver ion is negligible. Look at the calculation we did earlier. And if the combined method works, then we convert this multiple equilibria into a single equilibria. And the single equilibria is going to have a K that we call, these combined methods form these combined Ks. The combined K is going to be called KSPF. And KSPF is just going to equal KSP times KF. Yeah. And then we just have a single ice. We don't have to do multiple equilibria. Single ice table. But it'd be nice to be able to do combined, but we don't often get this scenario where we have a very small step 1 and a very large step 2. Except here. So we'll do a combined calculation maybe tomorrow. And so we just add ammonia. A typical question would be, how much ammonia, how many drops of ammonia are required to dissolve, let's say 100 milligrams of silver chloride. We can calculate how many drops that would be using the combined method in the ice table here. I'll do that tomorrow in class as an example. But for us, it's just adding ammonia. We keep increasing the ammonia, then we're going to dissolve it. And really, we didn't calculate how much. We just kept adding it until it dissolved completely. And so this dissolves the precipitate, and we end up with this. This is the reaction here. In the net, or you could write the 2 individual equilibria here. All right, and then in the next step, what do we do? In the next step, we add HNO3 to reprecipitate out the silver chloride. And so here, the HNO3 step, put here, this is not balanced. Just reprecipitates out our silver chloride. Yeah. So we could do this qualitatively here. Qualitative, it's just going to be just a Le Chatelet shift. So if we want to reprecipitate, I'm not going to write a precipitation reaction. What I'm going to do is I'm just going to write my KSP. actually, I shouldn't do it that way. Let's write the equation we had for the last step. This is not working. So it's the same thing, except we want to attack something on the left side now. And so the nitric acid will attack my ammonias. To form ammonium nitrate. K for this is very, very large. So all we're going to do is this, we're just going to do this qualitatively. So as the nitric acid attacks the ammonia, this is called free ammonia, this is called complex ammonia. The free ammonia concentration decreases, which shifts the equilibrium to the left. And so we're going to get a left shift of the equilibrium here. We're just going to do this qualitatively here. Okay. So those are the reactions for the first branch there. Let's go on here and take a look at the other branches here. So the remaining cations we're going to mix with ammonia ammonium chloride. So this is the decantate. And so we're going to take our decantate here. And let me drop it down here. This is a Henderson-Hasselbalch buffer. And the reason we're going to buffer the solution is we don't want the pH to get too high. We need to not allow the pH to get too high. The reason why is what we want is we just want the 3+ cation. So for example, we have iron 3+, aluminum 3+, and chromium 3+. And normally this takes 3 ammonias and 3 waters to precipitate out iron 3 hydroxide, solid. And the product of this will be ammonium. We'll form 3 ammoniums here. And so the more ammonia we have in the buffer, the more this shifts to the right. The more ammonium we have in this buffer, the more this shifts to the left. And so we're trying to balance it out. Obviously we want to maximize the amount of precipitate we get here, but there's a problem. And the problem is that, insoluble hydroxides, all hydroxides are insoluble except for which ones? Yeah. So as we recall, all hydroxides are insoluble except group 1, ammonium, and calcium, strontium, and barium. So iron 3 hydroxide is going to precipitate out. Aluminum will precipitate out. Should be 3 waters. Chromium 3 should precipitate out. But also some others. What were the other ones that we had? We had calcium. Calcium should not precipitate out. So calcium plus the ammonia yields NR reaction. This calcium hydroxide shouldn't precipitate out. Ammonia and water. Ammonia and water forms a little bit of ammonium hydroxide. Is it? So calcium is not going to react. Don't have to worry about that. However, magnesium should react. Magnesium, we do expect a reaction. Magnesium 2 plus 2 ammonias plus 2 waters. This is going to produce magnesium hydroxide, solid, plus 2 ammoniums. Now, the way we prevent magnesium from precipitating is Le Chatelier's. We make sure there's enough ammonium here to prevent it. And the nice thing is, it's different amounts. So for example, up here we need lots of ammonium in order to prevent precipitation here. Significant quantities of ammonium, actually huge. Whereas here for the magnesium, we don't require that much ammonium. And so the mixing ratio was important for that particular problem. You had to get in the right ratio in order to prevent precipitation of the 2 plus. In other words, this was buffered to prevent precipitation of this by limiting the amount of hydroxide that we have in solution. We can control the hydroxide concentration by either increasing or decreasing it by adjusting the buffer, by buffer adjustments. Buffer adjustments is you change the ratio. So for example, if we're looking at magnesium hydroxide precipitation, then we always do the KSP equation for that. So magnesium hydroxide precipitation involves the KSP, magnesium 2 plus 2 hydroxides. And then the hydroxide concentration is going to dictate, how this shifts one way or the other. The hydroxide concentration is going to be controlled by the This is a case where, we could either use the Ka or the Kb can be used for the buffer. Ka or Kb can be used to describe so weird. Each time I hit my button on this, it puts an E. That's the reason there are two forms of the Henderson-Hasselbalch. There's the pKa form of the Henderson-Hasselbalch and the pKb. The pKa yields the pH, the pKb yields the pOH. But if we use the Kb to describe it, in this case we'll use the Kb. Ammonia plus water yields ammonium and hydroxide. So by controlling the ratio of ammonia and ammonium, we can control how much hydroxide we have. In other words, the pOH or the pH. Here. By controlling how much hydroxide we have, that could limit the amount of precipitation. We just need to make sure that this is unsaturated. So we've got to keep the hydroxide concentration low enough that we don't exceed KSP, i.e. QSP has got to be maintained less than KSP for this. So we need QSP to be less than KSP, and therefore no precipitation, because it would be considered unsaturated. So just keep the hydroxide low enough that when you calculate the concentration of hydroxide, square that, multiply that by the magnesium, it comes out less than KSP. And we could do that. So it works. What, in effect, what we're going to do is we're going to separate out all these 3+ from the 2+ by controlling how much hydroxide and making sure that QSP does not exceed. Up here, for the 3+, we want QSP to exceed KSP. We have enough hydroxide there that QSP is going to be greater than KSP, and we get precipitation. And we want complete precipitation of these before any of these 2+ begin to precipitate. So complete precipitation before these would begin to precipitate. The 2+ cations. So that's magnesium. So what we're going to say is that we're going to get no reaction here because the KSPs are too low. QSP is too low. So there are two ways of doing it. We could do it qualitatively. You know, qualitatively is we shift this equilibrium to the left by increasing the ammonium concentration. Quantitatively, now the problem with chapter 19 is there are multiple ways of handling this. So I gave you the combined method, but in this particular problem, we wouldn't use the combined. We do two separate calculations. So if we did this quantitatively, what we do is we use the buffer, HH buffer, to calculate HH equation. We calculate the pH, figure out the pOH, and then figure out the hydroxide concentration. And then what we do is we do a QSP versus KSP type deal. QSP versus KSP. QSP is just the given magnesium concentration, usually like 0.1, and the given hydroxide based on the HH equation here, and we'll see. Now, if we want to be more quantitative, then we can calculate the solubility in the presence of that much hydroxide. This would be qualitative. Will we get a precipitate here? And so this is answering the precipitation question. Quantitative, what we do is we go back here and look at common ion effect. And so we do quant This is qual. Here. This is the next step. Or we do quant. Quantitative, I would just calculate the solubility in the presence of that amount of hydroxide. Now this is a buffered solution, so we would calculate the solubility in the presence. When we have a buffer, the hydroxide doesn't change. So the initial is going to be the same as the equilibrium hydroxide. Even if there's a change here, if there's a change, the buffer will compensate for it. And so what we do is we calculate the solubility in the presence of this. So this is plus S, this would be plus 2S here. So there is a change here, but the buffer compensates for it, and therefore it just reverts back to the initial. And this would be the S. So we calculate the S. That'll tell us the solubility in the presence of this. Well, that's magnesium. What other 2 pluses do we have? The other 2 pluses that we have are nickel and zinc. Both nickel and zinc form insoluble hydroxides. They're not the exception. So, for example, for nickel, we have to do the same thing. And for your report, you would just do this qualitatively. Here. So this is what you'd write. We're just going to take advantage of Le Chatelier, where we increase the ammonium and then shift this left. We're not going to do this qualitatively. Okay, and also zinc as well does this. This is tedious writing these over and over again, but insane basic one, but the more practice you get, the more you'll remember. So I'm going to write it out. Was that it for the 2 plus? Yeah, just magnesium, calcium, magnesium, nickel, and zinc. Okay. All right, so what we end up with is we end up with these 3 precipitates, and everything else will have no reaction with the buffer. And so these would be the 3 precipitates that we end up with here. Okay, then let's go on and take a look at the next step of this. Let's take a look at the 3 precipitates here. The rust, iron 3 hydroxide, the gray-green, chromium 3 hydroxide, and the colorless aluminum hydroxide.
You said this is our last day to do this lab?
Yeah.
I kind of have a long way to go.
Do you still have a lot of procedure left to do?
Only like 3.
You've only done 3? Step 3?
Like
Step 3? Oh, all right. Then we'll continue this more. You'll have to do this later. I'll stop now. It's been going for about, what, 1 hour? Yeah. Okay. So try to get as much done as possible. The unknown doesn't take that much time, actually, unless you get confused. It takes more time. Okay.